Newton's law of universal gravitation. Alright, so let's talk about the force of gravitational attraction between any two objects, or F sub g, or what I'd like to call the force of gravity. The force of gravitational attraction, or the force of gravity, is equal to capital G times m sub 1 times m sub 2 divided by r squared. Note that the force of gravity is in the SI unit of the Newton, as all forces in this class will have the SI unit of the Newton. Now capital G is called the universal gravitational constant, and that's equal to 6.67 times 10 to the negative 11 newtons times meter squared over kilograms squared, and it is always that value, which is why it's called a constant. M1 stands for the mass of the first object in kilograms. M2 stands for the mass of the second object in kilograms. And R is the distance from the center of mass of object 1 to the center of mass of object 2. Alright, now I'd like to talk about the force of gravity and Newton's third law of motion. Here's the Earth. Here's you standing on the Earth. And there is a force of gravity on you. I'm going to call this a person. There is a force on the person because of the Earth. And there is a force on the Earth because of the person. These forces are equal in magnitude, and they are opposite in direction. If we were to calculate the force on the person because of the Earth, we would use the universal gravitational constant, big G, multiplied by the mass of the person, multiplied by the mass of the Earth, divided by the distance between the person and the Earth squared. Now, what is the distance between that person and the Earth? Isn't the person standing on the Earth? So really what we're talking about is the center of mass of the person to the center of mass of the Earth, and that happens to be this distance here, what I'm going to call R. And for all purposes, that's almost exactly the radius of the Earth, so I'm going to put an R sub E. And so what we're going to do is divide that by the radius of the Earth and then square that value. Alright, now how would we calculate the force on the Earth because of the person? Well, using Newton's law of universal gravitation, we would use the universal gravitational constant, big G, multiplied by the mass of the person, multiplied by the mass of the Earth, divided by the distance between them, which would be the radius of the Earth squared. So as you can see, the force of the person because of the Earth is equal to the force on the Earth because of the person. The difference between them is that they are opposite in direction. Now if we define up as positive, we'll call it up plus y, then you can see that the force on the person because of the Earth is acting down, or it has a negative value. So every action has an equal and opposite reaction when we're talking about Newton's law of universal gravitation. Alright, now let's look at the law of universal gravitation a little bit more. Let's look at the magnitude of the force of gravity. And let's say that we doubled the mass of the person, so we put a 2 in front of the mass of the person. And let's say we doubled the mass of the Earth. And let's say that the radius of the Earth tripled. What happens to the force of gravitational attraction between the person and the Earth? Well, of course, whatever you do to one side of the equation, you must do to the other. So in the numerator, 2 times 2 is 4. And in the denominator, we actually have 3 that we need to square, so I get a 9 in the denominator. So if I double the mass of the person and I double the mass of the Earth and I triple the radius of the Earth, or the distance between them, I get 4/9 of the original force of gravity. Let's talk about the acceleration due to gravity using the force of gravity in Newton's law of universal gravitation. So the force of gravity, which is Newton's law of universal gravitation, is equal to the universal gravitational constant multiplied by the mass of object 1 multiplied by the mass of object 2 divided by the distance between the two masses. And let's just focus on the magnitude right now. Now, force of gravity, a person's force of gravity, is also known as the person's weight. So let's say we have a mass of the person times g, that's their weight, and let's say they're on a planet, let's say they're on the planet Earth. That would be equal to the universal gravitational constant, the mass of the person, the mass of Earth, divided by the radius of the Earth squared. Now, if you look at this equality I have, you can see that there's something we can cancel here. And what we can cancel is the mass of the person. So I'm left with small g, known as the acceleration due to gravity, also known as your gravitational field, and that's equal to your universal gravitational constant multiplied by the mass of the planet you're on, in this case Earth, divided by the radius of the planet you're on, in this case the radius of Earth. So the acceleration due to gravity on Earth only depends on the mass of the Earth and the radius of the Earth. It does not depend on the mass of the thing in free fall at all, and this proves it right here. So if I went to the moon, for example, the moon would have a different mass, the moon would have a different radius, and so my acceleration due to gravity would then change based on the planet I was on. So your acceleration due to gravity, or the rate at which you free fall, is dependent on where the location that you are at in the universe, but it absolutely does not depend upon your mass. Now, how does the acceleration due to gravity change on Earth, for example, if you're not near the Earth's surface? Say you're somewhat away from the Earth. For example, here's the Earth, here's Mount Everest, and here's you on top of Mount Everest. How does the acceleration due to gravity change because now you're farther away from the center of Earth? Well, the big thing that changes here is your distance from each other, from your center of mass to the Earth's center of mass. So we have the radius of the Earth, the radius of the Earth, but we also have the radius of what I want to call Mount Everest, because you're on top of Mount Everest, and those are the two values that we're going to add together to find the total distance between the center of the Earth and basically the center of you, but that's so small compared to everything else that we just say that's negligible. And so that would be the distance, or the radius, or the height of Mount Everest plus the radius of the Earth. So what does that look like in the formula for the force of gravity between you and the Earth? So we still get the universal gravitational constant, we still have the mass of the person, we still have the mass of the Earth, and the distance between you and the center of the Earth is now the radius, or the height, of Mount Everest plus the radius of the Earth, and we square that whole amount. So we're increasing the value in the denominator. This value becomes much larger, so that your force of gravitational attraction does become much less. How does this affect your acceleration due to gravity? Well, if we have your weight, which is the mass of the person, times the acceleration due to gravity, that's still equal to everything on the right side, which is the universal gravitational constant, the mass of the person multiplied the mass of the Earth, divided by that total distance of the height of Mount Everest plus the radius of the Earth, squaring that. Now, if you see here, something does cancel, and it is the mass of the person. So I am left with the acceleration due to gravity is equal to the universal gravitational constant multiplied by the mass of the person. If you notice here, the distance again between the person and the center of the Earth has increased, so the acceleration due to gravity has decreased. Looking at the acceleration due to gravity a little bit more, let's play around with this a little bit. So your acceleration due to gravity then is equal to the universal gravitational constant multiplied by the mass of the planet that you are on, divided by the radius of that planet squared. Now let's see, for example, the radius of the planet increased by some amount. Overall, what happens to your acceleration due to gravity? It decreases. Now, okay, so if we increase the mass of the planet, let's do that. What happens to acceleration due to gravity? That increases. One more example. Let's say that specifically we doubled the mass of the planet an object is on. And let's say we doubled the distance between the object and the center of the planet. What happens to my overall value for my acceleration due to gravity? Well, in the numerator there's a 2, and in the denominator there is actually a 4, because this 2 is within the parentheses and is squared from my exponent of 2 over here. So in essence, I get 1/2 of the acceleration due to gravity. Now I want to talk with you about orbit, free fall, and acceleration due to gravity. So here we have the Earth, and on top of the Earth we have Mount Everest. And on the top of Mount Everest we have a cannonball. Now, when we are measuring the acceleration due to gravity, or the force of gravity here, we need to measure the distance of the cannonball to the center of the Earth, and that's right there. And since we're talking about the Earth, let's go ahead and draw in Antarctica, near the South Pole. And near the top, we're going to have a couple continents up here. Okay, so there's the Earth and Mount Everest. Now let's say we shot the cannonball off with an initial horizontal velocity at some velocity, and then the ball falls under the influence of gravity and free falls towards Earth like so. Now there is an initial horizontal velocity here that has the tangent of that direction, but as we shoot the ball out faster, we try again, we shoot out faster, the ball covers more of a horizontal distance before it falls to the Earth in the same amount of time of, say, 1 second. Now, if we try it on the other side, first is the lower speed, it does the same thing, and then do a little bit faster, it does the same thing. And the cannonball, when it hits the Earth, makes little explosions. There we go. Okay. Now, eventually, you shoot out the cannonball fast enough so that in the, say, 1 second it takes to hit the ground, by the time it goes to hit the ground, you know what the ground does? The ground pulls away from it. So it keeps trying to hit the ground keeps pulling away from it, and before you know it, this cannonball, in the absence of air, this is when this happens, is in orbit. So in essence, when an object is in orbit, it is really free-falling towards the Earth under its own acceleration due to gravity. And the moon is no exception to this case. Speaking of the moon, here's the moon orbiting around the Earth. Here's the Earth. Now, if we apply Newton's law of universal gravitation, the Earth has a force on it. There's a force on the Earth because of the moon, and the moon has a force on it because of the earth. They are equal in magnitude and they are opposite in direction. If I make up in this diagram positive, then what I have is the force on the earth because of the moon is equal to a negative force on the moon because of the earth. The magnitude of the force on the moon because of the earth is equal to the universal gravitational constant multiplied by the mass of the moon multiplied by the mass of the earth divided by the distance between the center of the moon all the way to the center of the earth. And this is typically called the radius of the Earth-Moon distance. Now the moon is also moving in orbit, is it not? It is moving in what I call circular motion. It's moving around in orbit. And when an object is moving around in uniform circular motion, the net force acting on this object acts inward from the circular path, and it is called centripetal force. So this force on the moon, because of the earth, is also called the centripetal force acting on the moon, and these two values here are equal. So the centripetal force acting on the moon is equal to the universal gravitational constant, which is multiplied by the mass of the moon multiplied by the mass of the earth divided by the radius of the center of the earth to the center of the moon squared. Now, what is the formula for centripetal force? Well, the object that is moving around in a circle is the moon. That's the mass of the moon from our previous lesson, multiplied by the tangential velocity of the moon squared, divided by the distance between the moon and its center of its circular path, which is the radius of the Earth-Moon distance. Rewriting this on the next page, we have this expression. You see here that the mass of the moon will cancel, and something else cancels, and that is the radius of the Earth-Moon distance. So this 2 goes away, and that goes away. So I'm left with the tangential velocity of the moon squared is equal to the universal gravitational constant multiplied by the mass of the Earth divided by the radius of the Earth-Moon distance. Now, let's say I asked a question. I said, what is the tangential velocity of the moon? Well, all we would need to do here is take the square root of both sides, and I get the square root of the universal gravitational constant multiplied by the mass of the Earth divided by the radius of the Earth-Moon distance is equal to the tangential velocity of the moon. Please note that the mass of the moon is not important when we are determining the tangential velocity of the moon. What is important? Let's take a look here. The radius, or the distance between the center of the Earth and the center of the moon, that's important. And also what is important? The mass of the planet of which the object is orbiting, in this case the moon. So let's say, for example, we increase the mass of the Earth. Let's see if we can fit this in here. Let's increase the mass of the Earth 4 times. What ends up happening to the tangential velocity of the moon? It will double. Time for practice. Good luck with your practice, and remember this assignment is due the next time we meet. Have fun.